Hello, welcome back. In the next set of videos, I will talk about the union find structure. And then I'm going to show how to use union find to solve some of the LeetCode problems. The union find structure is very useful for maintaining disjoint sets. So what are disjoint sets? Here are two examples, 1, 2, 3, and 4, 5, 6. Notice that there's no elements in these sets that will belong to more than one set. So all elements are mutually exclusive. These examples that are not disjoint sets, 1, 2, 3, and 3, 4, 5. Notice that both sets share the element of 3. Graphs can be considered as disjoint set as well. Here are 4 examples of graph as disjoint sets. By the way, all these slides are available in the GitHub links below. Using the union find API, one can answer the questions such as these. So for example, here are 2 graphs. If you want to ask whether 3 and 7 are connected, the answer is yes. Connected here means that it's either a direct connection or indirect connection. If you ask whether 3 and 6 are connected, the answer is no. Suppose we want to call the union operation for the nodes 9 and 8, and after that, we ask whether 3 and 6 are now connected, then answer is true. At the code level, in the union find structure, each disjoint set is represented by a parent root node, and all nodes within the same set would have the same parent. So for example, here on the left, you have a graph, and to represent this in a union find structure, a node is picked as a parent. Here, the number 5 node is picked as a parent, and then the rest of the nodes in the structure will have pointers pointing to the parent. Please note that there's nothing special about the node number 5. Any of the nodes can be the parents for this set. It can be chosen randomly. Please note that the structure on the right, the arrows indicates pointers pointing from one node to the other. Now notice that such structure may take in another form, for example here, where you can have one node, for example number 9, pointing to a parent 7, and 7 in turn pointing to number 5. In one such a structure, there will be only one uber parent, the parents for that set. In this case, it's the node number 5. Notice the union find structure does not preserve all the attributes of the graph. The structures on the right do not carry any information on how these nodes are connected. They only say that these nodes are connected somehow, either indirectly or directly. Now here are examples of 2 union find structure, 2 sets. And if we want to do a union of these 2 sets, we just introduce a pointer, and that pointer would come from the parent of one set to another. Okay, let's talk about the union find structure at the code level. There is not a lot of code for the quick version of union find. There are 3 main pieces. First, we need a container to store the parent's information for each node in the graph. This container could either be an array or a hash map. Second, there is the find parents function, in which it will recursively find the parent of a node. The third piece is the union function, in which the find parent function is called for both nodes. And then there is just one liner in which the parent of one node becomes the child of the other. Let's take a look at an example in which we establish the union find structure for a graph. Here we have a very simple graph, and we are given a set of edges for this graph. Each individual array represents an edge. So for example, 3, 0, there's an edge between 3 and 0, and they're connected. To establish the union find structure, first we initiate the parents array. Then, using a for loop, we assign each individual node to be the parent of itself. As you can see, the representative of the array, the index is the node itself. The value of the array is the parents, such that the parents of 0 is 0, parents of 1 is 1, etc. Here is a graphical representation of the parents array, in which each node is the parent of itself. Next, we use a for each loop to loop through all the edges and perform a union operation on the 2 nodes for each edge. For this example, after we loop through all the edges and perform union operation for all the nodes, the parent array becomes this. We can see that all the values here are 0. So the parents of 0 is 0, the parents of 1 is 0, etc. Here's the graphical representation of the parents array. We can see that the 0 value becomes the parents for all the other nodes. The parents of 0 is also 0. And that's it. We have established the union find structure for this particular graph. Now let's take a look at another example. Here are the set of edges, and we are consuming these edges in that order, from left to right, 0, 1, 1, 2, 2, 3, etc. And after we perform the union operation for all these edges, the parents array becomes this. So the parents of 0 is 1, the parents of 1 is 2, etc. Here is a graphical representation of the union find structure for this particular graph. As you can see, the structure is really tall. Suppose if we're gonna do another union operation on the 0 node, and we're gonna find the parents for the 0 nodes, one can see that such iteration we have to go through the entire length of this set of nodes. So it's an O of n operation. Now suppose we take the same graph, but this time we shuffle the order of the edges in which they are consumed. We perform the union operation for all the edges, and then at the end, the parent array becomes this. As you can see, the values are very different from the previous iteration. And here is a graphical representation of the parent array. As you can see, the depth of this structure is a little bit shallower compared to the one from last time. So the point I want to make is that the order of the edges in which they are consumed matters, and that will dictate the depth of the union find structure. If we are using the structure for finding parent for each individual node, you can see that the operation would be the height of the structure. So it would be a big O of log n, in which n is the number of nodes in the structure. So using quick union find, we can see that sometimes we can encounter pathological cases in which the find parent operation would have a time complexity of big O of n. In addition, the order in which the edges are consumed matters. Changing the order of the edges would change the union find structure, and hence the time complexity for the find parent operation. The previous example was using quick union find. There is an weighted variant of union find in which the size of each component is being tracked, and in the union operation, larger components becomes the parent of the smaller one. So it can be proven that the complexity of this variant is consistently big O of log n. The code is very similar to the quick variant. One key difference is that we introduce another array, shown here as rank, in which we keep track of the size of each component. The find parents function is exactly the same as the quick variant, and the union operation, there's a little bit more code. Basically, it checks which one has a higher rank, and the higher rank will become the parent of the ones that are of lower rank. Let's return to the previous example in which we have a structure where the find parents operation can have the time complexity of big O of n. Now, suppose this example, we deploy the weighted variance of union find, and you can see the parents array becomes this. And the graphical representation of this structure is this. And you can see every node is pointing to the node 1. And certainly this is a very shallow tree. Okay, now previously using the quick variant where we shuffle the order of the edges, we got a structure in which the tree is feasible to use the find parent operation. Now, suppose we take the same set of edges and we subject them to this weighted union find operation. Let's see what we have. And we get something like this. Here's the graphical representation of the parents array. You can see we pretty much get a very shallow tree. Now for this example, the difference between the weighted variant and the quick variant is very subtle. For a much bigger graph, it is the case that using the weighted variant would generate a much shallower tree compared to that generated from the quick variant. So for performance, I use the weighted variant. For interview purposes, I will stick with the quick variant because it's very simple and there's not a lot of code to remember. As long as you can discuss with your interviewer and the time complexity and some of the pathological cases that can arise when you're using the quick variant. It is worth noting the union find algorithm can be further improved with path compaction. In the latter, every node will be linked directly to the parent node. This way, the find parent operation will be nearly a constant time operation. This is something that is not so difficult to implement, and it is also certainly something that you can discuss with your interviewer. In the GitHub links below, I have provided the C# codes for both the quick and the weighted variants of union find. Please take a look. In the next series of videos, I would use the quick variant of union find to solve some LeetCode problems. So let's have a quick recap before we finish off. First, we initiate the parents array in which each node is the parent of itself. The random time complexity for this step is O of n, where n is the number of vertices in the graph. Next, we look through all the edges and we do a union operation. For the union operation, because this involves the find parents operation, and the find parents operation on the average would have the time complexity of log n. So the time complexity for the for each loop will be e times log n, where e is the number of edges in the graph. Okay, we are done. Hope this is helpful and hope to see you next time.